Thank you, Meredith. Thank you everyone for joining so early in your time zone. Thank you. I'd just like to express my gratitude to the other co-leads of the marine ecosystems and this physical oceanography working group who joined this session, helped organizing it. My name is Linja. I'm a co-lead at the CIS working group, along with Matthews here, and Angela, and Xinhua, and also I think Nathan and Ignatius couldn't make it today. And of course, special thanks to our speakers, our fantastic speakers today. Professor Emily Eidam, who is Associate Professor at Oregon State University, and Dr. Nicole Jeffery, who's a Postdoc Research Associate at Los Alamos National Laboratory. We wanted to organize this session with a theme that connects all of the different working groups because we thought it would be so nice to do something a bit more interdisciplinary and to focus a bit on the complexity of the issue of sediment transport. So today the speakers are going to focus on the physical aspect, but we're also hoping to maybe develop this into a rolling session where we can highlight different aspects of this theme in the future if there's interest and excitement about it. Thank you everyone for joining. So I think Emily is going to kick off with her presentation just now on large-scale erosion of the inner Beaufort Shelf. Thank you.
Great, thanks. I appreciate the chance to come and chat about this today. About this subject today, and I'm looking forward to hearing Nicole's talk as well. So I wanted to talk about sediment transport dynamics on the inner Beaufort Shelf, and I'm going to be focusing on Harrison Bay, which is this region north of the Colville Delta here in the southeast corner, and then it's west of Cape Halkett, which is on the left side of the screen here. So a lot of the motivation for this work comes from pretty extensive research that has been done on coastal erosion in the Arctic. There have been many studies over the last several decades highlighting that the Arctic experiences some of the most rapid coastal erosion in the world. And I just wanted to highlight here a brand new paper from my colleague Roger Creel, who did some really interesting modeling to show that shorelines in the Arctic are retreating not just because of permafrost bluff erosion, but they're also experiencing effects of sea level rise, as well as permafrost subsidence. And if you put all those together and forecast several decades into the future, you see that there is an expected substantial land loss in areas around Cape Halkett, possibly many tens of kilometers of coastal retreat. So this raises a really interesting question of where does all this material go in the marine environment? Is it piling up on the continental shelf? Could it attenuate waves by doing so, or is it getting broadly dispersed? And then there's a whole host of implications from that for people studying ecology and benthic habitats and food webs. So we wanted to find out where the mud was going. We wanted to think about whether depot centers were forming. That's a big term in marine geology. We know that there are big hotspots of mud deposition on sites like the Oregon Shelf that receive sediment from the Columbia River, shelves offshore major rivers. And with all the bluff erosion in the Arctic, we would expect to find that mud on the shelf. Or maybe it's broadly dispersed, but we would really like to understand the mechanisms of transport, whatever erosion is happening or whatever deposition is happening. So we received some NSF funding to conduct field studies primarily in 2021 and 2022 on the RV Ukpik. We also had a great chance to team up with Jim Thompson's group during his CODA project and go out on Sekuliak in the 2 years before that to get some trial data. And our main field campaign conducted in 21 through 22 included some shallow water moorings on the inner to middle shelf. Unlike other moorings that have been located at the shelf break, our moorings were located at less than 20 meters water depth to really try to capture that inner shelf sediment transport. We collected a whole host of seabed samples. We collected a lot of geotechnical measurements with my colleague Nina Stark at University of Florida to think about shelf erodibility. We did some lead-210 isotope analysis on some short gravity cores. We collected a lot of multi-beam data, some chirp data, and then teamed up with Jaap Nienhuis at Utrecht to do some morphodynamic modeling of the shelf and then a sort of synthetic Colville Delta. All that data is available on the Arctic Data Center, and a lot of these results are in published papers, and I'll share a link to that at the end. We spent a lot of time looking at seabed properties, and that was really fascinating. Most of the shelf is heavily scoured by these ice keels that form as the undersides of the pressure ridges between offshore and landfast ice. And that causes a lot of local disturbance of the seabed. It makes it very hard to apply isotope techniques to look at sediment deposition. So to look at sediment deposition, we had to leverage other tools in our toolkit, ideally moorings that allow us to look at active sediment transport during the summer. So these are the mooring sites from 2022, and we were able to conduct open water season deployments, which meant that we were able to have them out for about 5 weeks. Since it's such a challenging place to do small boat work, it's hard to extend it much beyond that. These were all small coastal moorings. Some of them had Nortec aqueducts. A lot of them had RBR sensors, salinity, temperature, turbidity, other properties. We collected a lot of data, and in a 15-minute talk, I can't walk through all of this, but this is in a paper that's in revision now, and I'm happy to share more of this offline. So I want to skip ahead to the highlights of what we found from the mooring data about where sediment is going in the summer. And the main story here is the wind-driven dynamics. The wave climate is pretty weak early in the summer. It grows a little bit throughout the season as the sea ice is retreating, and Jim Thompson's group has done a lot of nice work there showing that transition in the wave climate during the summer. But it's microtidal and the winds are very important. And when the winds come from the west, they drive some setup. And this has been observed in other parts of the Arctic coast as well, notably over by Tuktoyaktuk. And that setup drives a little bit of what we could reasonably call downwelling. So this near bed flow that is flowing across the shelf in a seaward direction. And there's a little bit of wave energy during this time, and that creates a little bit of sediment resuspension, and those downwelling flows advect some of that material that's coming in from bluffs and rivers across the shelf toward the ocean, toward the deep sea, which we might expect. However, in this part of the shelf, which is not true in all sectors of the Arctic, but on the Alaskan shelf, the dominant winds are from the east and the northeast. And that's really important because that creates coastal set down. And the strongest waves tend to come with those stronger winds. And so we have strong wave energy during periods of coastal set down. That coastal set down drives a little bit of upwelling, so near bed onshore flow. And that near bed flow flowing toward the coast, paired with waves that have resuspended sediment, serves as a mechanism to transport sediment in a landward direction. That's a little bit unusual. We tend not to see that in a lot of continental shelf settings. In a lot of settings, the dominant sediment transport during strong wave events is offshore. The Oregon margin is an example of that. But there are some examples. The Atchafalaya system, so the coastal areas west of the Mississippi Delta, have a high sediment supply, and that is also a strongly wind-driven system where when you get strong wave energy and strong sediment resuspension, wind-driven currents actually help push that material toward shore, and that forms some of the Cheniere plains of coastal Louisiana, which are big, muddy coastlines. So if you put that together, this is sort of our conceptual picture of the dominant sediment transport pattern in the summer. Rivers and bluff erosion are bringing in sediments. A lot of that sediment input happens during spring breakup, and it gets stored on the inner shelf due to this convergence of currents paired with strong wave resuspension during northeast winds. And that sediment tends to converge inshore of about the 15-meter isobath. So probably at about 8 to 15 meters water depth is where you're getting a lot of this summertime storage. Granted, we surveyed for 5 weeks during an open water season. But I think that this is a pretty typical circumstance because if you mine the ERA 5 climatology data for the winds, you can see that those northeasterly winds have been dominant going back many, many decades. And northeasterly winds, if you look at the ERA wave hindcast, correspond to bigger waves. So we could reasonably assume that this is happening every year, that you have this strong inner shelf sediment focusing. So there should be a depot center, right? I think that's what we hypothesized going in, that this rapid coastal erosion would be leading to a large storage of mud on the inner to middle shelf in this, somewhat wave limited environment, low wave energy environment. And that would have a lot of implications for coastal morphodynamics because that sediment could serve as a source for new barrier islands to form if the supply increases. And it could also serve as a site of carbon storage. So we were really interested in trying to find other ways to validate that. And we tried collecting some cores and analyzing for lead-210, and we found almost none. And that's not entirely surprising because there's a lot of ice scouring. But even with the ice scouring, if there was a lot of sediment depositing, we probably should have found some excess lead signals somewhere. So we looked at another tool. We had all this nice new multi-beam trackline data. And Chris Zimmerman from Fish and Wildlife had recently gone back and recorrected all of the 1950s Coast Survey bathymetric charts, which people are still using for navigation. It's kind of the best available bathymetry there. And so we were able to do some differencing between our multi-beam data and Chris's data. And my student Adrian made this map of erosion and deposition along all of our multi-beam tracks. And everything in gray is within our uncertainty bounds. We don't really want to put an estimate on that. The blue shows very modest deposition on the middle shelf, but the red is showing that there is substantial erosion on the inner shelf. And that erosion is most dramatic over by Cape Halkett, which we know is retreating, and on the Colville Delta front, suggesting that the Colville Delta is also retreating. And I know there's other work on subaerial Colville shorelines that also indicate that it's probably retreating. So this, if we quantify this, we can see up to 3 meters of erosion on the inner shelf in 70 years. That's a lot of seafloor erosion. This was actually predicted by USGS researchers in the 80s. Reimnitz, Barnes, Kempema, and others did an amazing body of work up there. They were doing a lot of marine geology as the oil industry was booming. And I really like this conceptual graph from Reimnitz. It's got a polar bear and a kayaker and a cabin in there and a caribou. And he looked at the rates of shoreline retreat, and he hypothesized that if the shelf remains in sort of what we call this morphodynamic equilibrium, so if the shape of the shelf isn't changing a lot, which, you still have a lot of sea ice during the year, it probably isn't, as the coastline retreats, the shelf should basically follow it, and you should have this what's called self-similar backstepping of the shelf. That's a geologic term, meaning the shelf is basically just following the shoreline. Because the shelf is concave up, that means that the greatest vertical erosion at any location should happen on, I said middle shelf here, I should have said inner shelf. So closest to shore, as you can see in this diagram, is where you would have the greatest erosion. And that's exactly what we saw. And granted, the data in this graph is a little bit qualitative, but we had fun sort of overlaying his predictions on our actual measurements, and they were almost identical. If anything, we measured a little bit more erosion than he predicted, which makes sense if you think that shoreline retreat is accelerating. But how does the erosion happen? We just showed that during the summer, sediment converges on the inner shelf. So why aren't we finding it there? And we can again go back to the 80s, and these USGS researchers hypothesized that entrainment in sea ice during the fall, entrainment of sediment in sea ice during the fall, and then rafting of that sea ice in the spring could actually account for the total removal of the annual input of sediment from rivers and bluffs. So in the fall, you have big storms while the sea ice is forming. Those big storms pump sediment into the water column. That sediment gets entrained in frazzle. It becomes part of the ice pack, as shown in this dramatic photo of a block they cut out near Prudhoe Bay. And then in the springtime, that muddy ice rafts away and forms, beautiful ice rafted debris deposits that are such an important part of the geologic record in the deep ocean. So we have a new project funded through OPP. Maddie's leading this project, and we're looking at wave and sea ice interactions, but we're also going to focus on going out and collecting observational measurements of what is happening with the sediments during that fall storm season. It's a really tough time to measure. We're going to take Sekuliak out. We're going to take small boats out. And we're going to try to do a really good job of collecting a robust observational data set showing what material is in suspension, and then trying to understand how that material is getting bound up with the frazzle and incorporated into the sea ice. And we're going to be running a 1D model that Chris Sherwood developed a while back to try to start linking our measurements of what's in the water column to a quantification of what's going into the sea ice. And then I'm really excited that Mackenzie Jewell is going to be joining us and teaming up and bringing some of her excellent sea ice modeling skills to see if we can do some particle tracking to see where those sediments might be going after they get entrained in the sea ice. So it should be a lot of fun. I love this photo because it shows this very high zone of turbidity, almost exactly where we measured summertime sediment convergence a few years ago, kind of that 8 to 15 meter depth range. So that's kind of the sweet spot for storing sediment, and then it's in a really good place for the wave resuspension to impact it and pump it into the sea ice. We have quite a few papers out. The first couple of papers are the really cool modeling papers that my students did together with Jaap Nienhuis, if you're interested in coastal morphodynamics. And then we have some more observational papers about the data sets that are coming out. And again, all that data is available on Arctic Data Center now. So I'll wrap it up there. Thank you very much.
Thank you so much, Emily. How interesting. Also, this historical component that you showed and the diagram. I don't know if someone already has some urgent question now. Otherwise, I don't know how you prefer, Emily, if to take them now or to keep them for the discussion. If there are any questions at this point.
Happy to chat more during the discussion.
Nice, thanks. Okay, then we keep going with Nicole. Thanks so much. Who's going to talk on the role of sea ice in Arctic marine sediment transports?
Thank you, Lenny. Let me see if I can share. Should be able to, right? You can see my screen okay? Okay, let me just start with a quick introduction. Thank you, Lenny, for the intro. I haven't been a postdoc researcher in quite a long time. I am working at Los Alamos National Lab, and the work I'm going to talk about now is related to the Interface Project, which is a Department of Energy project with a lot of collaborators. It's a multi-institutional project. And I wanted to start off a little bit to give a background about that project to help motivate the work that we're doing. Interdisciplinary research for Arctic coastal environments began in 2019, and our goals are to evaluate and improve Earth system and human system modeling in the Arctic region. So we're really a model development and analysis focused project. And we're doing this to understand the coastal regions, coastal systems, and in particular, those systems that are most vulnerable. And what we did, and what we have been doing since 2019, is focusing on specific areas for research. We have a focused effort on permafrost hydrology, looking at using advanced terrestrial simulator, so a process level model, but trying to understand larger scale with that model. We have a coastal erosion modeling effort that is led out of Sandia. The Arctic coastal erosion model is really trying to understand how to model permafrost bluff failure. We have sea ice and wave modeling efforts, not just a sea ice and wave independent, but also the coupling interactions of the two to help us quantify what's the role of sea ice and waves in the coastal zone of the Arctic. And finally, we have a biogeochemistry effort as well. We model biogeochemistry in the sea ice, in the ocean, and in the sediment, seafloor benthic layers. And these are independent efforts. At the same time, they are tied together. And one of the connections between all of these efforts is sediments, whether you're thinking about what's changing the erosion of the coastlines and the melting of the permafrost. How are these sediment sources changing that are ending up in the ocean? Where are they ending up once they get into the ocean, given that we have a changing sea ice dynamics? And how does that impact things like the carbon stored at the benthic? So this sediment piece is tying things together. We have just started work on it. I'm not going to have a lot of finalized efforts, but I'll show you where we're going with this. First, sea ice and sediments. I always like to start with some pictures, and I'm always amazed. As a model, I'm always amazed when I look at the pictures because I don't get to see it as often. The first picture I have here on this side, I hope you can see my cursor, is in the southern Hudson Bay. This is a region that's tidally forced, and this paper describes this sediment resuspension process. You have a flaw lead forming near the coastline. You have tidal forcing that's resuspending the sediments, but at the same time, you have a lot of new ice frazzle formation. Everything's being incorporated. That's why you get this really thick sediment picture. This other picture is an aerial photograph This is from a paper by Hisatomo Waga, who's using satellite to help interpret what the sediment loads of the sea ice are. And you can see the brown is the sediments. Okay, so sea ice and sediments, what are the impacts? Not just on the sea ice, but how does the sea ice impact the sediments? So there's impacts in both. The first is what you see from looking at the pictures. It's going to impact your spectral albedos. The blue line here is clean ice, and the green is what happens as you increase the sediment load. You see that decrease in the albedo. That changes your radiative properties in your sea ice. So you get, of course, light absorption, you get less reflection. You also see less light penetration, so it impacts the biogeochemistry within the sea ice. It impacts the biogeochemistry under in the ocean as well. There's other impacts for biogeochemistry. These sediments often carry iron, they carry micronutrients, they carry biogeochemically active material. The sea ice itself can turn around and change the river plume dynamics. Here's just one example with pressure ridges that dam the river around the Mackenzie and change the dispersal of these nutrients just by its presence. Emily did a great job talking about ice-impacted seabed, the keels and the keel scours. We also see changes in the particle distribution along the sediment floor. Instead of purely ocean regions where you see a dispersion of particle sizes, here you get gravel deposits in all sorts of different areas. Finally, we have changes in the seafloor sediment accumulation rates because of sea ice transport, which impacts your carbon burial rates. And that's one of the things we feel like we're able to maybe get a look at in this particular project, the long-range transport. This is a great image by Carmack et al. In the 2015 paper. The blue arrows are the ones that are probably of most importance in terms of sediment. What you're seeing is the shelf region, surface transport of sea ice through the transpolar drift. And there's evidence that this is changing as we see more melt occurring in the shelf regions, and that's going to change your sediment transport of that ice rafted material. Okay, what are the sources in the Arctic? Interestingly, rivers, which globally tend to dominate your sediment sources, 72 to 89% is a global estimate. That's quite different in the Arctic because coastal erosion can be really large. Here's an example in the Laptev Sea, something like 70% of your erosion sources. The other really important process is this resuspension, of course, because often coastal erosion is happening at a time when you don't have sea ice, when you have sea ice retreat. So it's that resuspension process that's occurring during ice formation and other times of the year, particularly in shallow polynyas or wave-driven and tidal-induced regions that allows for the incorporation. There's other processes, glacial meltwater plumes is important, dust, aeolian transport, and of course you have the ocean transport, which I'm really not going to talk about in this, but it also is incredibly important for the Arctic. The two mechanisms we take a closer look at is frazzle ice formation and anchor ice. Frazzle ice, which can happen down to more than 100 meters deep, but often happens in these shallow areas, very sticky, so it adheres to objects, adheres to each other, and that's an important mechanism for new ice formation. And anchor ice, this is a picture from the Southern Ocean. This is ice that has nucleated and adhered to the bottom substrate. If it's fine sediments, it's going to pick that up and send that into the sea ice. Thicker, heavier objects like gravel, it may adhere to. It can pick up benthic organisms as well. I mean, all of those things are possible with anchor ice. Okay, so for our perspective, what is our strategy to take a look at the impacts of sea ice on sediment transport and how it connects with the different pieces of erosion and the fate of these sediments? And what we're doing is we're leveraging the E3SM, the Energy Earth Exascale Earth System model. And it is a powerful capability. And I'm only going to talk about the sea ice piece here. Of course, there's the atmospheric, there's the land and the ocean components as well. But if we just look at the sea ice model, we can see that it already transports several types of ice rafted material. Okay, there are dissolved and particulate biogeochemical tracers vertically resolved in the ice model. This is an example of primary production in the sea ice. It accepts dust and black carbon as well that's transported. It accepts material sources, not just from the atmosphere, but the ocean as well. So that capability is within the model. It has radiative feedbacks of the dust and black carbon already built into the model. That's this figure here, where the black lines is showing the sea ice volume in the northern hemisphere compared to the same simulation, but without radiative feedbacks in the red. And we have much improved thickness and extent in our recent model, our version 3 model. That's this middle image here, where you can see the ice is piling up properly against the coastal zone off of Greenland. So we have this strong capability. Another capability we have is a diagenetic model on the seafloor of the ocean. This is like about a 30-meter depth where we do the biogeochemistry, and we've recently coupled that to the ocean biogeochemistry. So the ocean organic carbon fluxes, the ocean bottom sources now impact on that diagenetic model, the benthic model that we have for the Arctic. So a powerful capability, but with some severe limitations. Okay, particularly at the boundaries and in the shallow coastal waters. So our model resolution, and here's some example of what we're doing in the latest version, is 20 to 30 kilometer grid scale. That means the minimum depth is only 20 meters. Okay, much of what you were seeing is less than 20 meters. All those details that we talked about and that Emily mentioned, that's happening at less than 20 meters. So we can't even get down there with this particular model. We also have a very simple ocean frazzle ice parametrization, and we have no explicit sinking tracers in the ocean model. So some challenges, but we can make some progress. And here's the first attempt we did using impasse sea ice, where we applied a surface ocean sediment mass concentration at the river ocean input cells. And we were able to define a sediment flux using the sediment load observations from the Arctic rivers. impasse ocean, the ocean model never sees this concentration. It's only picked up by the ice model. So it's passed directly to the ice model. And this is likely what you can see as a lower bound for transport. And I'll just show you what we see, because you can see a little bit of that transpolar drift, I think, already there. I'll do it one more time because it's kind of cold. This is work I did with a summer student. Oh, it's freezing on me. That's what I get for trying to do it twice. Okay, let me see if I can, oh, it's hanging. Okay. Darn it. I don't know how to get out of this. I'm just going to escape for a second and see if I can. It is hanging on me. Okay, I'm going to stop sharing for a second and then I'm going to come back and see if that does it. Okay. Okay, let's try again. Apologies for that. Okay, here we were. I'm not going to show it again. Oh, there it's going again. Okay, we'll skip past it. Recently, we've thought about a second attempt, and this is using both impasse sea ice and impasse ocean. In this case, we applied an ocean sediment mass flux now to the ocean model. Again, we use the same river runoff flux and the same sediment load. This is now passed as a tracer into the ocean model with a very small sinking velocity. We don't have a proper evection scheme yet to do anything larger than this. So this would be like unaggregated mud. You could think of it as a mostly suspended kind of sediment material. We also modified the fragile ice formation to allow for pickup of sediments in the interior of the ocean by adding a porosity for that fragile ice. And we coupled that to the sea ice model, so that the sea ice model picks up that material either through fragile or congelation growth. And this now likely overestimates transport in a way. It does not keep the sources, there's no resuspension, it doesn't keep the sources on the shelf. Now I hope I can show this, and it's not gonna end. This, on the left side, you're looking at the ocean sediments. What the ocean model does for these sediments, it's also receiving material from the sea ice itself. The sediment source is entirely at the river. There's no coastal erosion, there's no resuspension. On the right, you're going to see what the sea ice does as it picks up that material. And again, you can think of this as sort of an upper bound now. There's no, the sources aren't nearly as strong in the coastal regions. You see a lot more dispersion of this source of the material, and you see a buildup where the sea ice builds up in these regions. Okay, where are we going with this? So we've kind of got bounds now for understanding transport. We do see some of the transpolar drift within the sea ice model itself. You see it in both, but you see it much stronger when you just look at the sea ice model. What we need to do is add a sinking advection algorithm that is not restricted by the CFL condition for multiple sediment tracers. We then need to couple the sources and sinks of the sediments at the seabed with the diagenetic submodule. We need some distinct sediment tracers in both the sea ice model corresponding to the radiative properties. We can use some of what we already have. And we'd like to extend our sediment sources to coastal erosion, given some estimates from the coastal erosion work that we're doing, that Sandia is doing. Finally, and this is really important, we need to increase the ocean coastal resolution. And this is work we're doing with the E3SM project, including reducing that vertical minimum depth beyond 20 meters. So we can really start to think about how to parameterize those processes that we know are so important. And that'll involve some multi-phase coupling and land-fast ice representation. Okay, apologies for the errors, but that's all I have.
Thank you so much, Nicole. It was super fascinating to see, and thank you for taking us into the interface project and showing us where it's going in terms of sediment transport. And I'm sorry for mixing up your position. I saw you laughing when I introduced you, so I realized I made a mistake. Thanks so much, both of you. I think Maddie kindly agreed to take on the discussion now. So I'm looking forward to some good questions and some diving into the topic further.
I think people can either raise their hand if they have questions or post them in the chat like usual, but I can also just ask a lot of questions if no one else has them. Maybe Emily can start, maybe has a question for Nicole.
Yeah, Nicole, thanks. That's a really amazing model. It's great to see the whole Arctic represented there. As far as the sediment in the sea ice, there are a number of papers going back a few decades where people have taken, a single ice core or discrete sets of ice cores and melted them to look at the sediment content. Have you had a chance yet to try to validate what's in your model against any of those observational data sets?
So I haven't done that yet because I really do think, it's interesting to see the transport within those models, but we are really looking at broad bounds within what we're able to model at this point. So I don't know how trustworthy those numbers are. It's definitely something we need to do. In particular, there is some now satellite estimates of at least what surface ice has sediment loads, that we can use that to help validate. So I'd like to get something a little more realistic before I try to pin down.
Yeah, it's a hard problem too, because the discrete ice cores, it's so spatially variable. Those aren't very representative in themselves, but it's kind of the best we have. And with the satellite data, do you have any sense of, do people have estimates of like what thickness of ice they're able to quantify the sediment load over? Is it like centimeters or tens of centimeters?
Yeah, that's another problem with the satellite data, is that you can get estimates of what say the sea ice thickness is. Right now they're showing estimates of what the surface sediment value is. Our model, I don't know that we'll get a surface sediment value with our model the way it's designed right now. Most of the way the model works is that sediment is going to stay in the interior. We're not even going to see it at the surface. So we have that issue with our model right now. So yeah, it's a tricky problem. I will use sediment cores. That's what we do for the biogeochemistry. And even though it's very spotty, we still do that. Yeah.
Yeah, that's a tough problem. Thanks.
Yeah.
That sort of leads into a question I had, so maybe I'll jump in. I guess I was going to ask about, I mean, it seems like you do have the sediment being radiatively active in the model already. Is that true? You're adding different classes, but it is.
So the dust and black carbon is radiatively active within the model.
Okay.
And right now that's coming from the atmosphere.
Okay. So, but are you treating the sediment the same way or no?
I'm not at this point. We could.
Oh, okay. Okay. Because I was going to say, so part of my question was about the like variability, but then so also because if it was active, then you might start to see it potentially accumulate at the surface, right? Because and that's what we see. Like in reality, part of why you see so much in the surface in the satellite imagery is that as the kind of that albedo feedback kicks up, it accumulates at the surface, and so maybe you would see that some in the model too.
So right now, and we have the same issue with the biogeochemistry doing radiative feedbacks, is that the melt takes the material away. So we don't have a mechanism for retaining the sediment in the upper parts of the ice when it melts. So there's some subtleties in terms of how it's modeled that aren't appropriate for sediments, and that we need to think about how to do that properly, because that is a real impact. You do see the sediments at the surface when things start melting. And right now the model's just not capable of doing that. Which will mean that sediment radiative feedbacks is going to be a next thing. You know, it's not going to be the first thing we look at because we're going to be missing that.
Yeah, that makes sense. Yeah, I think we're using some of your same code to try and include microplastics and obviously dealing with the same thing. So, does anyone, I don't know, I don't see anyone else's hands raised. If anyone else wants to jump in with questions, asking them. I mean, I think a clear point also between the two talks was kind of like this gap in the coastal zone. I mean, you kind of mentioned that as a clear direction to go with the modeling, but I guess maybe a point of discussion is there, currently, do you think there's things that we could be looking for on the observational side to help better constrain what those fluxes should be from the coastal zone, and like understanding what drives when and where that sediment's getting into the ice? Or do you think it seems like the base level is just being able to resolve that area, but maybe there's also just like a kind of boundary condition that could be coming from observations? Or how do you see that?
Yeah, so I mean, I looked at the work that Emily's doing, and yes, there's a lot of detail in the inner shelf that we maybe won't be able to capture. But what we are looking for is that flux boundary. So we want to capture the net effect of what is actually leaving that zone. And I think the scales are about right. You're looking, you know, around I think 20-meter depths. It's not that we don't have a grid cell that's under 20. There's something there. It's just going to be the source. We're not going to resolve it. So that data is going to be useful. All that data along the coastline is useful for the model. And we are thinking about ways to downscale, not just within the model. We're doing that with waves. For instance, we're taking the wave model and then downscaling that information for local regions to do the coastal erosion modeling, which is on a very small scale. And then looking at characteristic topologies of the coastline to upscale that information to then look at transport in the model. So we don't have one model that does it all. I don't think we're going to quite get there, but there are pieces, all the pieces that you guys do when you really get down to doing the observations that do inform the overall picture.
Yeah, lots of cool opportunities. Joshua, I don't know if you have a question. You can unmute yourself.
Thanks both of you for wonderful talks. So I have a quick question for Nicole. So in the model, you mentioned that the frizzle ice is able to pick up the sediments. So I wonder, is it only at the bottom layer of the ice, or it can be like multiple layers in the ice?
So the frazzle, right now, the way we're doing frazzle, the standard model only, forms frazzle wherever the ice is, the temperature is super cooled. So at depth in the ocean model, I think down to about 100 meters. And it only changes the temperature and picks up salinity. So the current model doesn't do even the biogeochemical tracers. So we've since been improving that because I've been thinking about the sediment problem and the biogeochemistry. So what I've put in is a porosity term that wherever frazzles forms within the ocean, and that doesn't have to be at the bottom layers, wherever frazzles formed, it takes the concentration of sediment at that location times the porosity, we're using about 85%, and then bringing that up to the surface. And that's where the sea ice picks things up right now. So there's a lot of work to be done to do something like that properly. There's no mechanism for doing density changes because of sediments, and that's really important as well. So it's pretty crude right now, but it's a start, and you can get information even from something pretty crude, I think.
Cool, thank you.
Any other? Oh, sorry, go ahead.
Since no one is asking questions here, so I have another question for Emily. So you showed your work for the summertime, the transports, and then you have an upcoming exciting project study, the fall time sediments. I wonder for the springtime, like it's very like understudied. So I'm wondering like what is so like the during the springtime, it's the landfast ice still there, and then but it's also the freshen the springtime, like a huge amount of sediments are dumped into the ocean at that time. So like what are the states during the springtime? Like are they just stay below the sea ice, or how does the timing of the breakup affect the sediment transport? So yeah, I posed a couple questions here, so just want to look see your insights.
Yeah, that's a really great thought. We have a study from the 60s on the Colville that tells us the sediment load. It'd be nice if we had newer studies. There's been some satellite work, but we're still lacking a lot of good observational data on the rivers. But if you assume that up to 60% of the annual Colville load comes out in 2 to 3 weeks during spring breakup, that is this huge injection of material in a short amount of time. And a couple thoughts about that. From the modeling perspective, my student Caroline Cooper put together a 2D Delft 3D model to sort of simulate sediment transport and erosion of an Arctic delta like the Colville under the influence of sea ice. And we wanted to know how the delta morphology would change if there's less sea ice each year and more wave energy. And less sea ice is a very timing sensitive issue, right? Are you talking about less sea ice during spring breakup when all that mud's coming in? Are you talking about less sea ice in the fall when you have strong wave energy? So we tested some of those questions, and observationally in the springtime, when that plume comes out, it can flow over the ice and then down through tidal pressure cracks to form strudel scour. It can flow under the ice, and that seems to be the more common case. And when you have that ice there, it actually routes that plume water farther offshore than it might go otherwise, and it actually forces more distal sediment deposition. But the sediment deposition, it still ends up on the middle shelf. And then during the summer, that material gets worked back toward the inner shelf and gets stored for presumably fall sea ice entrainment. If you take away the sea ice during the spring freshet, now we see more dumping of sediment in the model very close to the delta. So that sediment is still available on the inner shelf for wintertime transport. And if you turn up the wave energy, we were able to start making the delta erode, and you don't necessarily need a lot less sea ice. You just need a little less sea ice in the fall during the storm season to get the delta to erode. As far as observations, we have proposals pending to try to go work in the spring. It's a very high risk time of year, but one of the things my lab group has done is develop very cheap turbidity sensors that we don't mind putting in high risk environments. And we could put those in on drifters. We could seed the area with drifters in the spring before and during ice breakup and plan on losing some to try to get some of those measurements. We're also teaming up with Jim Thompson to build our turbidity sensors into his microswifts, and those are another great platform that you could put out in the spring, like from a helicopter or something, to try to get those data. And then the little coastal moorings that we deployed are pretty robust. They worked pretty well. And at this point, I would be comfortable putting those out very close to the Colville Delta in the fall and hoping that they'll survive the winter and get some data in the spring. And I think we know a few areas where we could realistically do that, where we'd have a likely chance of getting them back. So we're getting there.
So how deep is the mooring? Are they like only at the bottom, or it's like a couple of depths?
We can design them either way. If we're going to leave them out over winter, we often put a little mast up so we have an OBS that's not wallowing right at the bed, like maybe a meter above the bed, so we can have a pretty low profile, or we can put a surface float and have a chain of sensors, or we can do we have a proposal in where we want to do a mid-water column float, so that we're getting like the lower half of the water column, but we're at less risk from ice.
Cool. Thank you.
Great questions. Are there any other questions for either of our speakers or points for continuing discussion? Well, I think it's been really interesting, and it's clearly a topic that's of interest, but also I think both these topics have made it really clear that there's like a lot of areas for us to work on as a community and a lot of potential points for discussion and interdisciplinary application of this kind of work. So hopefully maybe this is something we can cover again in future meetings. If there's more speakers that you'd like to see on these topics or kind of related areas, please feel free to suggest them to us. Before we close, I just wanted to mention a couple things that are on the horizon for the CIS community of practice. We have an upcoming meeting. Oh, Angela just posted it in the comments, but in the chat. But so our next meeting is on June 17th on the state of sea ice forecasting. And then this summer, we're also planning for an upcoming meeting as part of the data sovereignty series on caring for Arctic data and indigenous data. The data that still to be determined. So hopefully we'll see many of you again for those as well. Yeah, I think that's it for me. Thank you again very much to our two speakers today.
Thanks, everyone.
Thank you so much.
Thank you.
Hey, have a good day.